Hi there, and my name is Jiantao Zhang, and this is the final presentation of my course project for pattern recognition. This project is about doing experiment on playing Atari game with DeepQ network. The DeepQ network is an architecture based on the deep reinforcement learning algorithm. Here's the instruction, and the deep reinforcement learning is a combination of reinforcement learning and deep learning. And briefly, it can learn to perform just like a human, get the input of any kind of sensory information, like sound, images, and then output one or a series of proper actions. Therefore, we can say that the deep reinforcement learning may give computers the ability to learn only by themselves. In this project, I built up a DeepQ network architecture to learn to play Atari video game. And this whole architecture is built in Python using the TensorFlow library. The game environment is provided by the OpenAI team, which contains hundreds of game environments for the reinforcement learning. And here's the outline of my project. I used 4 algorithms here in my project to build up the network. Actually, the DeepQ network is a combination of the Q-learning and the convolutional neural network. And the Q-learning is a part of the reinforcement learning algorithm. So all these 4 algorithms used in this project. And firstly, let's talk about the reinforcement learning. The reinforcement learning is a machine learning algorithm, and it contains an agent. Here, the brain is an agent, and the outside environment here, the Earth. And on each step T, the agent will receive the observation OT from the outside environment, and then it will choose an action AT to do to the outside environment, and then finally get a reward RT feedback from the environment. The reinforcement learning is based on a Markov decision precise. The main point of this Markov decision precises can be described as that the future is independent of the past, given the present. So, every current state contains all relevant information from the history. The Markov decision precises contains a state set S here, the state side, and action side A, and the matrix of state transition probability R, and a P, and a reward function R. The gamma here is a discounted factor, which means how important the future will be to the current state. Here you can see, here is the reward function of the current state. The current reward function is based on all possible rewards, of current state, which is small rt, and also the future reward function is rt plus 1. And if gamma is close to 0, it means that the future will have little influence on this current state. And if gamma is close to 1, then the future reward will be very important for the current reward. Okay. So for the state of step 0, here the S0, then we will choose an action A0, and we will get a reward R1 from the next state S1 doing the action A0. And on the state S1, we'll choose an action A1 and doing the and get a reward R2 doing the action A1 to the next state S2, and just keep going on and going on, and finally we will end up with the final state Sn, and this is how the Markov decision precises goes. Okay, now let's talk about the Q-learning. The Q-learning is a value iteration of reinforcement learning, and a Q-value is defined in a Q-learning to represent the maximum discounted future reward. So the Q-value here is actually the discounted reward function of each state, and it can be updated in this way. So for each state T, make a choice of action, and for all possible actions AT, find out the maximum Q value with this action, and then get the next state as T plus 1. So we will have this maximum Q value. And the lambda here is a gamma talked before, is a discounted factor, and the alpha here is learning rate. So we can update the Q value in just in this way. Now let's come to the DeepQ network. DeepQ network is developed by the DeepMind team in their paper, and since input observation is a RGB image which contains all informations in Atari games. So the DeepQ network will use a convolutional neural network to pre-process these input images and get the Q value from these observations. So here is the detail of the architecture of the convolutional neural network used in the DeepQ network. The CNN has 3 convolutional layers and 2 fully connected layers. The original input of this CNN is in size of 84 times 84 times 4, which means there are 4 continuous state observations input to the for every iterations to the convolutional neural network, and the final output size is based on the action number. For example, if you are playing a game and this game has 4 actions, for example, so the output of this convolutional neural network should be set to 4. So it should be set to 4. And here is the architecture of the convolutional neural network used in DeepQ network. And we can see here there are convolutional layers and fully connected layers, and the final output is the Q value of all the possible actions. For each action, it will have its corresponding Q value outputted from the convolutional neural networks. Yeah. So here is a loss function and the Q value. The loss function should be calculated using the convolutional neural networks. We can get the maximum Q value just from here, from all the output actions and their corresponding Q value. We can find out the maximum Q value and its corresponding action, and then get the next state using this action. So here, this is the maximum Q value we get from the convolutional neural networks. And the loss function can be calculated. Just use a square error equation, and in a very simple way. The Q here is the current state. It means the past state, the past Q value of the state. And so there are some important tricks used in DeepQ network to improve its performance. One of them is the experience replay. The experience replay will store all past and the history experience in a replay memory, and instead of training the DeepQ network use the experience of last step, it will train the DQN using a small batch of experiences stored in the memory. So each time when the memory will output a small batch of random experiences, and that will be, for example, the experience of 1 minute or 2 minutes before to train this DeepQ network. And this method will mitigate the correlations between the current state and the past state. And second trick is a target update. We can see here, this is a tensor board, and this is a graph of the architecture built in my program. So here, the right network, which is here, is a target network, and it is also a convolutional neural network with the same architecture as the left one. So the left architecture and the right architecture are the same convolutional neural networks. The right architecture is called the Q network, and the left architecture is called the Q network, and the right architecture is called the target network. So these networks, the target network's parameters will not be updated for every step, but the Q network's parameters will be updated for every step. The target network will provide the target Q value to calculate the loss function, which here we can see the target network will provide this maximum Q value for every action you choose. And so, and when the loss function is calculated, we can use here we can use the root mean square propagation and this optimizer to minimize this loss function and update all the parameters in the Q value. So the precise of this target update is using the target network to get the maximum Q value and use the maximum Q value to calculate the loss function and use this optimizer to minimize the loss function and finally we will update the Q networks with this minimized precise. And here we can see how this precise is going. So here is the input, and this is the convolutional neural networks. And the output, and this is the Q value, is the output of the network. And then use the gradients. Here the gradients. Here we use the root mean square propagation and optimizer to minimize the loss function get from the output of the convolutional neural network. Then when we in the process of minimize this loss function, we will update all the parameters in the Q networks, the weights and the biases in the Q networks. Okay, and now we'll go back here, and this is all the technical update to do. And the third trick is exploitation and exploration. The exploitation is make the best decision given the current information, and the exploration is gather more information. So the gradient exploration method is used in a DeepQ network, and there is a epsilon, which is a gradient probability epsilon is defined in the DQM, and every time when we need to choose an action, firstly we need to get a random number between 0 and 1, and if this random number is larger than epsilon, then the best action will be chosen as next action. The best action is the action which has a maximum Q value, and if this random number is not larger than epsilon, so then a random action will be chosen as the next action. And the best action is called the exploitation, and the action with the random action is called the exploration. And so the gradient probability epsilon is initially set to 1.0, which means all actions are chosen randomly at the beginning of the training. And then the epsilon will smoothly be decreased to 0.1 during the training process. So when the epsilon is 0.1, there are 90%, and the 90% probability that the action will be chosen the best action, which is exploitation, and there are 10% that the DQN will choose a random action to do the next step, which is called exploration. So here is parameters used in this DeepQ network. We can see here the mini batch size is 32, which means that using the experience replay, we will every time get a size of 32, get a set of 32 small batch of experience stored in the memory, and use this small batch of experience to train our DeepQ network. Okay, we can also see here the target network update frequency. The target network will be updated every 10,000 steps. So for every 10,000 steps, then we will copy all the parameters in the Q network to the target network, and for any other steps, the target network will not be changed. Okay, so finally we'll talk about OpenAI. OpenAI is a toolkit for reinforcement learning research, and it includes a growing collection of benchmark problems that expose common interface. So the OpenAI is a Python library contains a hundreds of gaming environments, and we can get this information from the all the environment with the OpenAI Gym. For every actions we choose, then the output of the environment will be the observations and the reward and down, which means if this episode is over, for example, if you're playing a game and if you die for this episode, and the information is all other informations included in this environment. So I implemented the breakout environment in my experiment, training with deep Q network, and the observation of this environment is a 210 times 160 RGB image. And the final reward of this environment is the score you get in this game. And this environment has 6 different actions. So the DQ of my experiment is trained to play this game, and it cost me more than 100 hours to train this network for 50,000 episodes, and that was for a very long time. So now here is the experiment result, and we will show you how my experiment performs. So this is the code I used to build up my architecture and train my episode. So fine, here is how my network performs in playing this breakout video game. So the board here is a agent, and we can play an action of moving left or moving right, or a double move of any other actions. And the reward is the goal you get for each action. If the ball falls down, you will get zero reward, and if the ball hits the hit the wall, you will get 1 point as a reward. The experiment result shows here. The first figure is the average loss value of each episode, and this result shows that the loss value comes to smooth as it begins to train. But I think I still need a longer training time and more episodes to train to get a better performance and make the loss value to be lower and lower. And the second figure is the average maximum Q value. We can see here this is an increasing curve, which means that the Q value in this network is increasing as it is being trained. So you can see that this deep Q network performs better and better. The third figure is the total reward for each episode. The total reward will, as you can see, is increasing as the network is learned to play this game, and the duration time for each episode is also increasing curve. These two figures also means that this network performs better and better. Okay, so now that's all about this is my project experiment. So we can see that as the number of training episodes increase, average loss value comes to be smooth and stable. Average maximum Q values increases steadily, shows that the performance of this network becomes better as training going on. The total reward and duration time of each episode shows that it is learning to play this game better and get higher score and hold for a longer time. And in this project, I made an experiment playing an Atari game Breakout with deep Q network architecture. And the result of this experiment showed that this architecture can successfully learn to play video games only by itself, and the performance getting better and better. I believe that with enough training time, the performance of this network video games can even beat mankind performance. Okay, that's all. Thank you.